Our last example was a little unrealistic because it's not like you can always drive at exactly the same speed. For example, if you're on the freeway, you'll probably travel slower through towns where there's a lot of traffic and faster between towns. Below is a graph of distance versus time. I'll give you a minute to copy that down. Now, we don't know what the car's speed at any particular point was. In other words, if the driver glanced at the speedometer to see how fast they were going at that moment in time, you can't tell from this graph what that is. What you can tell is that over the entire 5-hour journey, well, it took 5 hours to go 200 miles. So the average speed was 40 miles per hour. And here I'm using our familiar old DIRT formula, distance equals rate times time, and solving that for rate, we have rate equals distance over time. So in the course of the whole journey, average speed was 40 miles per hour. We can say that even though we don't know what the speedometer would have said at any point on the freeway. Can we draw a line whose slope gives the average speed? Yes, we can. It's the line that joins the beginning point to the ending point. The slope of that line would be, as usual, rise over run. The rise is 200 miles, the run is 5 hours, so we have 40 as the slope. So again, we have the slope of a line giving an average speed and rate of change being basically the same thing. A line that joins 2 points on the graph, like this line that joins our beginning point to our 5-hour point, that is called a secant line. Not to be confused with anything you might have learned about secants in trigonometry. A secant line, probably we should write that down. The secant line joins 2 points on a graph. And the point we're making here is that the slope of the secant line gives the average rate of change or average speed over that interval. And just as a little preview, as I mentioned before, we don't know at any particular point what the speedometer would have said, at least not from this graph. One of the big tasks of calculus, one of the big problems that historically motivated the development of this thing called calculus was exactly that. Trying to figure out, if you have a distance versus time graph, how can I tell from that graph what the speed was at any point on the graph? Not the average speed over a whole interval, but the speed right at that point. And that, by the way, is called instantaneous speed or instantaneous rate of change. which is what I think of as speedometer speed. If I glance at the speedometer in my car, I'm thinking that's the speed I'm going at this exact moment, which isn't necessarily the same as my average speed over the entire trip.